but it's 8 a.m. in US. It's already 9 p.m. in Seoul.
Yeah.
Okay, maybe we can start. Because we have 4 talks this morning, afternoon. And I'm not sure if Sergey is able to join. I know Dimitri can. So we start off today with a talk by Yongxia Teo from Seoul National University. And he's going to talk about virtual distillation with noise dilution. So we look forward to your talk. Yongxia, you can start anytime you are ready.
Okay. Thank you. So I will talk about basically a small result that is part of a few projects I started at Seoul National University concerning variational quantum algorithms and error mitigation. So basically, I started these projects last year, so I'm still a newbie in these matters. So any constructive input or criticism is always welcome. So let me, for the benefit of those who is not that familiar with variational quantum algorithms, let me just briefly introduce them. So in short, these are called VQAs. And we are now in the so-called noisy intermediate scale quantum era, or NISQ era. And during this period, we are particularly interested in a class of problems that may be carried out by noisy quantum circuits and a classical computer. So this is basically the class of function optimization problems, where the cost function to be minimized is in general a function of multi-qubit observables. It's not restricted to these problems, but these problems are pretty popular when considering such devices. Now, if we evaluate such functions on a classical computer, and if the number of qubits is actually large, the number of qubits being n here, then the computation time scales exponentially in n typically. So as you can see from this example graph, you see that actually this graph shows the average computation time of observable expectation values, which are relevant when we want to talk about, let's say, minimization of the eigenvalues of a Hamiltonian of a system. So a solution to improve the computation time is to replace the classical function evaluation part in the optimization step with quantum circuit sampling. However, there are also other practical aspects such as sampling errors, which we need to worry about. But in any case, these methods are known as variational quantum algorithms by definition, because they make use of a classical computer and a quantum circuit. And an example of a VQA for function optimization is the so-called quantum eigensolver, which is pretty well known now. And this is basically the problem of finding the ground state energy of Hamiltonians, describing electronic structures of chemical molecules. Or you can call this QAOA. I forgot the full name of this, but basically it refers to the optimization problem in combinatoric problems studied in computer science. There's also another class of VQAs that we are perhaps also very familiar with. This is actually quantum machine learning. And it's a kind of VQA that trains quantum circuits to learn data mappings And it also involves minimization of cost functions. So these are the two popular VQAs that people are really interested in nowadays. Now, because we are using quantum circuits, noise is always present. So in this work, we focus on two very common noise models that occur in qubit systems, in qubit circuits. The first is the photon loss channel. And this channel is acted independently and identically distributed to all qubits. So the error term you see here is actually the vacuum state, which is orthonormal to the original noiseless qubit state. And this is an important observation. So a little bit of a comment for photon loss treatment. So the treatment of photon loss can be a bit sophisticated if you want to, but we shall simply discard the non-coincidental data collected from the output of the circuit. So basically, this means that whatever quantum information that is dumped into the vacuum state cannot be accessed from the qubit space. So this is typically what experimentalists do. They consider only coincidence counts. And the second channel that we are interested in is the Pauli channel, which is present in, for example, delay lines in a typical photonic circuit where you have polarization perturbations or errors. So the error term that you see here, which is basically, as you can see, is a collection of Pauli operator actions. And these error terms are typically non-orthogonal to the qubit state. And this is a major difference from the photon loss channel. And we will see that this gives very different characteristics in the results that we shall see. Now, we also focus on noise channels that have very small error rates. So if you have a pure state labeled like this empty cat and bra refers to the target pure state. And if you have a very small error, then the noise channel will essentially map the target state to a mixed state such that it's actually a linear combination of the original target state with weight 1 minus epsilon. Epsilon is the error rate. And the error term over here, which can be basically any operator, which is also a function of the target state, weighted by the error rate epsilon. Okay. Now, then first we need to mitigate these errors because we have noise channels present. And there exists basically a zoo of techniques for mitigating errors. Now, it is actually not the business of this talk to compare these techniques because none of them are perfect anyway. But in this work, we need to at least choose one that is basically analytically accessible. And for this, we choose virtual distillation simply because it's a good candidate and it can mitigate errors without assuming the type of noise model. And rather recently, in a PIX quantum paper, it has been shown that virtual distillation can be implemented rather feasibly with shadow tomography, at least for low order virtual distillation. So let me explain what virtual distillation is. So it's basically born out of a very simple consequence of linear algebra. So suppose we have a noisy state. We have already seen this expression already. And then if one can transform rho prime into basically the new state that you see here, which is the original noisy state raised to a power of an integer m, followed by a trace renormalization, then if epsilon is small enough, we see that this result in the limit of large m, m being the order of the virtual distillation, gives us a state that is pretty close to the actual target pure state, the ideal target pure state that we would like to have. So this is basically virtual distillation. And we, again, based on what I just said, this virtual distillation, it's virtual because you can indirectly implement it either with an external circuit or you can do some kind of classical data post-processing with the help of shadow tomography. And to compare the quality of the error mitigated state, which is this one, and the ideal target state, we make use of the mean square error as the figure of merit. And this average is basically the average over all possible circuit parameters. And this general figure of merit is especially relevant if we are minimizing functions starting from a randomized circuit parameter C. So this figure of merit quantifies the average quality of error mitigation for at least the first few steps in the optimization strategy. Okay. So this is virtual distillation. I need to explain the second part of the talk, which is noise dilution. Now, ordinarily, if you have ambient noise, this ambient noise acts globally on the circuit. So it is actually pretty impossible to control how the noise acts. But let's say if we focus on peripherals or accessories that are used in conjunction with the circuit, such as, delay lines, then we know that noise corresponding to a delay line, let's say if I have a delay line over here at the end of the circuit, then the noise coming from the delay line, which is the isolatable noise, will occur mainly over here, not over here, at least the significant parts of it. So for instance, if you look at this figure, so if we have a 4-qubit circuit and we have a delay line that we need to use of an overall error rate, which has an overall error rate of epsilon, we can either put the delay line over here at the end of the circuit, or we can chop the delay line or split the delay line into parts. Basically, the number of noise layers here is given by LERR. So here, if we basically split the delay lines into 2, which means LER equals 2, then we can distribute these 2 parts across the circuit like this, or we can distribute these 4 parts across the circuit uniformly like this, where the error rate is now divided by the number of layers. So basically, physically speaking, if we have a delay line and if the error rate is modeled according to this expression, which is the typical case in physics, typical form, then for small decay rates, we can basically imagine that noise dilution is nothing but the physical splitting of the delay lines or any passive component you have that is modeled according to such a formula for the error rate, such that it's split equally according to either the length or the traveling time. In this case, the traveling time for the delay line is tau in this case. Okay, so this is noise dilution. And a relevant application to noise dilution is when we want to design a quantum cluster. So let's say if we have a quantum cluster consisting of a collection of circuits, each may be accessible by a user. So one user will pick one circuit and perform computation. And at the end of the computation, we would like to send the qubits to the detectors. But suppose that the detectors are limited. They're expensive. We can't have many of them. Then we really need delay lines for photonic cases. We need delay lines to delay the qubits. And it is up to the administrator to actually decide on how to rearrange these delay lines across the circuit. So in this work, we study whether noise dilution, or basically a good Spanish friend of mine suggested another name for this, which is noise homeopathy, is whether such dilution or homeopathy is beneficial in terms of isolatable noise robustness. So whether chopping the delay lines and distribute them equally across the circuit is beneficial in terms of the mean square error. Now, before I show you the results, I would like to just state that there is a premise to obtaining these analytical results, and that is that we consider that these individual circuit blocks that you see with which noise dilution happens, they are thick enough so that they have at least order polynomial depth with respect to the number of qubits, such that these Ws, these circuit blocks, are approximately 2 designs. So this is the assumption that we make to acquire the analytical results, but it's not necessary in practice because, as we will see numerically, even for shallow circuits, the numerical results actually fit quite well with the analytical ones, the analytical results for the mean square error. So let's look at the analytical results. First, we have the 2 channels over here. And as you can see, for the mean square error, it's this. For the loss channel, and for the Pauli channel, is a bit complicated. So let me just explain a little bit what these results mean. So for the loss channel, because the vacuum state, as you recall, is orthonormal to the qubit state, it turns out that because of this, the MSE is actually proportional to epsilon to the power of 2m. This is actually it's already known, so to speak, in earlier studies of virtual distillation, that the mean square error is proportional to epsilon to the power of 2m. So the mean square error actually drops exponentially with the order of the virtual distillation as m goes to infinity. So, but on the other hand, if you look at the Pauli channels have non-commuting error terms, right? So the mean square error does not go to 0 as m goes to infinity. In fact, the Pauli errors are persistent here. And we see that if the virtual distillation order is larger than, say, order 2, there is basically no improvement to the MSE. So this is, you may argue that this is well known, but what I think is interesting right here is that for both channels, the more diluted the noise is, the smaller is the mean square error. So basically the mean square error drops monotonically to 0 with respect to LERR because of the reciprocal dependence. Okay, so basically noise dilution actually helps. So for the remaining slides, I'm just going to show you a few graphs that illustrate this idea. So I'll just show you a prototype, and it's the same for the Pauli error. So for the photon loss channel, you see that this y-axis is in the log scale, and the mean square error, which is d, all drops exponentially with respect to the virtual distillation order. The markers here represent the actual numerically simulated points, and the dashed curves are the theoretical fits that came from the earlier analytical expressions. So if you look at these graphs, you see that the mean square error actually drops monotonically with the number of diluted layers. And here, the different color graphs just represents the different number of qubits here plotted until 4 qubits. And these four, basically the last 4 graphs are actually a combination of results from these two graphs in a different way, right? So this is basically the mean square error with respect to the epsilon, the error rate. And this is photon loss, and these are the Pauli errors. Basically, they are the same. The only difference is that now you see that there indeed, because of the persistence of the Pauli errors, you find that the mean square error doesn't go to 0 exponentially. It tapers or desaturates. So it confirms the analytical results. Now, these are for 2 design circuits, right? We can actually loosen up the requirement. Of course, analytically, it's not really possible to derive results without assuming the 2 design approximation. But here we can do some numerical simulations of what would supposedly be like if you have a quantum cluster. So let's say if you have a quantum cluster and each cluster is like a 4 qubit circuit. And we can also simulate what happens when you have a delay line of a certain physical length or a certain physical time. Here, we measure the delay line in terms of the time, the travel time. So you see that the results are basically the same. And we are considering in the simulation shallow circuits. So these W's have only 2 layers. 2 layers basically means that you have, so each layer represents basically a single qubit array and a C0 array over here, and then you repeat it 2 times. So it's a rather shallow circuit, and you see that the fit is very accurate for the photon loss channel. And also this is the case for the Pauli errors. There is perhaps some slight inaccuracy due to the non-commutativity, which requires a higher order error term to be more accurate, because we truncate the mean square error to only 2nd order in epsilon. So that's the reason for the inaccuracy. Okay, so this is a very short presentation, and so I will just conclude now that basically if you have a peripheral, and the suggestion is that if the peripheral is a passive one, because if the peripheral is sort of rigid, and that means that if the accessory cannot be shifted around, then noise dilution perhaps may not be of any use for that case. But if you have a delay line, and if you really want to implement a delay line for the quantum circuit, then because the delay line is a passive component, you anyway have to delay the qubits. Then you have a choice of how you want to wire the delay lines across the circuit. And it turns out that noise dilution, or homeopathy, is beneficial in terms of the mean square error. It's more robust against these isolatable error sources from the delay lines. And another perhaps side result could be that for small error rates and with the help of noise dilution, even persistent errors can be mitigated rather effectively with just an order to virtual distillation technique. So you don't need, at least for these two channels that we've tested, you don't need anything higher than second order virtual distillation method. So finally, what I want to say is that this is one of the few works that we've been working on, and these are already published works, and then we also have something lined up in the future, in the near future, hopefully. Hopefully there's no delays. So if you are interested in these topics, stay tuned to the archive. And yeah, thank you all for your attention.
Right, thank you. Are there any questions from the audience?
I have
You can just unmute yourself. Yeah, sorry. Go ahead.
Thank you for your talk. Could you please name the software packages used by you for numerical simulations?
Oh, that's easy. MATLAB. I didn't use Python for this because it's a rather simple simulation. So I did not use any packages for this. Yeah.
Thank you.
Yeah.
So typically in this algorithm, one of the major errors comes from the gates themselves. So if you have gates error, is that taken into account?
In this work, no. So in this work, we focus on the study of noise dilution, which means that you have the freedom to basically split whatever components that's causing the noise. And we are trying to see, because, okay, so let me tell you, the honest origin of this work comes from many of the studies in Nature Communication papers where people are considering layered noise environment, which comes from, as you know, after each entangling gate, there will be an error. So if you implement the gates in layers, then the errors will be in layers. So this is sort of a side project to see what happens if we can actually control the noise, the number of layers that you can have for the noise. And the only sensible application, at least for now, is the application with delay lines, which are passive isolatable sources. Yeah, so that's really the point of this study. I was actually trying to see whether one can actually do something with active switches, but even active switches is a bit difficult because for active switches, you need to place the switches over at, let's say, a beam splitter that needs to be that is needed to merge, let's say, 2 qubits together. You cannot really just shift the active switches however you like. So active switches is sort of out of the story. But if you have really any other practical applications, especially if you know of any other experimental situations where this is relevant, I would be good to know. Yeah.
Right. Are there any questions? I don't see. So let's thank Yong-Sia Teo for his wonderful talk. Thank you.
Thank you.
And then we welcome Stefan Atterman. You can share your slides. Stefan. Thank you.
Yeah, hi. Do you hear me?
Yes, yes.
Okay, let me just maximize this. Okay, do you see my screen?
Yes.
Okay, thank you. So today I will speak about optimizing states for quantum enhanced interferometry. Now, this work was done with my PhD student, Karunesh. So this is the outline of the talk. Basically, I'll do some introduction to be sure that everyone is on the same page. And then I'll basically discuss the 2 states I'm considering, namely the well-known and popular states, coherent plus squeezed vacuum and double squeezed vacuum input. So what is the motivation behind this work? Giving a limited resource in terms of average number of input photons, the task is to optimize an unbalanced Mach-Zehnder interferometer in order to reach the best possible phase sensitivity. And we want to do this in two scenarios. One, when there's no external phase reference available. I'll explain that in a minute. And B, when this is available, which are two different scenarios. So when could this prove relevant? When you do some sensing, imaging, biological imaging, photosensitive samples, and so on. Or if you technologically limit it by N and you want to use this resource as good as possible. So globally doing this, it's quite challenging. So we pick two states, but you'll see in a minute for very good reasons. So let me first introduce notations and other stuff. So since we're discussing an unbalanced Mach-Zehnder interferometer, we have to parameterize the transmission coefficients and so on. So this is the scheme we're using. It's actually the thing we discussed last year in a paper in LPHYS'23. And basically, we use these pseudo angles that prove to be very useful for compact writing for the transmission coefficients of the first and second beam splitter. And then the phase sensitivity, we use just the usual phase sensitivity, error propagation formula. And then the different detection techniques we'll consider, you see them to the right. So basically usual stuff like difference intensity, parity, homodyne, and so on. Now, the quantum Fisher information is a very important concept. Why is so important? Because this gives us the best possible phase sensitivity with what's known as the Kramer-Rao bound or Kramer-Rao lower bound. And I'm using the quantum version of the Fisher information, so the QFI, quantum Fisher information. And since we're discussing just pure states, the word is pretty simple, and it's just basically 4 times the variance of the operator that's relevant for the phase shift you have. And in our case, it's the number of operator in the arm 3, so that's quite easy. Important point, the QFI totally ignores the measurement scheme. So QFI stops somewhere in the middle of your interferometer. And so it will, let's say, optimize over all possible detection schemes we can imagine. Now, there's a supplementary problem. If you just apply bluntly the QFI, you'll just get 2 good results. And the reason is that the QFI doesn't say, hey, are you able to measure a global phase? He assumes yes. If you don't want to measure a global phase, it means you don't have access to an external phase reference. You have to kind of throw out the extra information you have. There are other means to do it, but I'll focus on this one, the 2-parameter quantum Fisher information. So basically, we introduce 2 internal phase shifts, although at the end, we make 1, 0. We switch from the phi1 and phi2 to the sum and difference. Then we create this quantum Fisher matrix. And then we have the same quantum Kramer matrix inequality. Now, this is well known. It's not tight. One cannot optimize for all, but we're just not interested. We want to optimize just for the different measurement, because we want to measure phase differences inside the Mach-Zehnder. So then we focus on a single element from that matrix, and we just want to saturate it. And so if we define F2P, the difference matrix elements minus the sum difference squared over sum, then we can define quantum Kramer-Rao bound, which is relevant for this 2-parameter. And this will apply when my detection scheme does not have access to an external reference. Now I'll relabel what I explained before, and I'll call this the single parameter QFI, 4 times just the variance. And so these are the 2 matrices we'll use to give the best possible phase sensitivity that I can get in the 2 cases when I have and I do not have access to an external phase reference. Fine. So the first state we picked is probably the most popular state. is coherent squeezed vacuum. Why did we pick it? Well, because, for example, you have this paper of Lang and Caves where they said, look, you have an interferometer. They took it balanced. They took no external phase reference possible, so the 2-parameter QFI. They said, I have a coherent input. I don't know what state is the other one. What is the best state? And they proved it's squeezed vacuum. So if you have a resource in terms of average number of photons, someone forces you to use a laser, which is quite current, then you should use a squeezed vacuum in the other entry. Good. So we can define now quantum optically this input state. We'll use just regular displacement and squeezing operators. Throughout this discussion, I'll consider that we are always using the optimal input phase matching conditions, which is given by this difference of phases. Quite often, authors just put all phases to 0. That's also a valid choice. Now, this is a very popular input state, I said, and I just listed the number of results with it. I mean, there's just way too many to list them all. So what we want to answer, given a coherent plus squeezed vacuum state, and my resource is n bar, the average number of input photons, what fraction of the coherent power should I put so that I optimize my phase sensitivity, case A, if I don't have access to an external phase reference, and case B, if I have access to an external phase reference. So this is my definition. I'll redefine everything in function of this F alpha and N bar. And well, the 2-parameter QFI has been reported over and over again in the literature. It optimizes in the balance case, quite expected result. And then if we rewrite it in terms of F alpha and N bar, you got the expression you see there. And now it's easy to see the extremes. If N goes to 0, you obtain that the optimum fraction of coherent power is 2/3. So you should put 2/3 of your power in coherent and 1/3 in squeezing to get the best scaling. If N goes to infinity, the optimum ratio is half. And this is a result which was reported in the literature without too much proof. Now, actually, if you compute from the 2-parameter QFI, you differentiate it in respect to F alpha, you get a third order equation, which you can actually solve. The result is pretty long and ugly, but you can find it. And amazingly, you have this closed form result where you can say, look, give me N, I'll tell you the optimum fraction of coherent input which you should put so that you get the best possible result. And you see the curve there with the limits we already said. And so 2/3 and half. How is the scaling going with this? So I optimized now my 2-parameter QFI. And as you see, I start roughly at the shot noise scaling. And slowly but surely, I mean, this is a log plot, right? It goes much faster. This is really log. Around N equal 1, I start to just shoot up. And then we continue with this Heisenberg scaling. What happens if I have access to an external phase reference? Well, then the 2-parameter QFI doesn't apply anymore. And you have to apply the single-parameter QFI, which is a little bit more ugly, more long. And, well, we can just do some algebra and obtain the expression. However, in this time, if we try to optimize it, we always get that the optimum is F alpha equals 0, and the Mach-Zehnder is totally degenerate. So basically, our state will just simply morph into a single squeezed vacuum. So you just don't use coherent. Now, of course, you can force balance, say, yeah, I don't want to unbalance my Mach-Zehnder. What happens? Well, if you just crank in the numbers, you see that you get exactly the same result. Now, in this graph, I picked an N, a low N, because that's the interesting case. High N are easy. And I said, fine, let's just vary F alpha and find the optimum T that maximizes my QFI. So this is what we did. And then on the lower one, I just plotted the QFI. And as you see, indeed, the optimum we obtain when F alpha is 0. However, for the two-parameter QFI, what we obtained from the equation I showed you before, which for this case is 0.56, that's where the two-parameter QFI is yielding the optimum result. So then we try to see, can we just actually reach this result? And yeah, I mean, there are detection schemes that approach this. For example, parity is showing quite good results, although suboptimal. Balanced homodyne detection is quite suboptimal, but not very far. And then if one detection scheme is optimal, it is quadratic homodyne detection, which is basically you square the X operator. And there's a recent paper that actually applied this without knowing that they applied this. They just applied squeezed vacuum, as you see there. Their Mach-Zehnder simply collapsed, because if they were to optimize this scheme I'm discussing, they should have obtained F star alpha 0 and the angle of the beam splitter pi. So they just shoveled in the squeezed vacuum through their sample, and they just homodyned it, and they kind of simulated the X squared by doing post-processing on the X operator. Now let me discuss the second state. This is also, I mean, there's a reason why I discussed it. The same authors, year later, they proved that if you have a balanced Mach-Zehnder and you exclude fixed, I mean, they also discussed this, but I'm discussing just the variable photon numbers. So if you exclude the fixed photon numbers, so that's the Fock states, the optimum you get is by 2 squeezed vacuum. So this is the input state. Now this time I define Fz as the ratio about the average number of squeezed photons in port 1 over the total one. And the purpose is basically the same. What fraction should I put so that I optimize my phase sensitivity? So once again, we have the expressions. We discuss, we maximize them, and it's quite easy to see that the optimum for the two-parameter QFI always maximizes in the balance case. And there's a special case, FZ05, meaning that you put equal squeezing, which will prove, yeah, one thing I forgot before going here, I always use the optimal input phase matching condition, which says that the two squeezers I have are in antiphase, like theta minus phi is pi. That's very important, because if you don't use this, many things complicate. So then we get this Heisenberg scaling, which is well known. And interestingly, if I plug FZ05 in the first expression, it simply collapses to the last one, right? So it seems that the beam splitter has nothing to say, and I'll discuss this issue in a minute. Now, the full expression for the single parameter QFI is quite long, but I have it in the appendix. So if you're interested after, I can show you other slides. Now, if I have lower squeezing in the port 1, it immediately collapses again. So my Mach-Zehnder becomes totally unbalanced, and I get this super Heisenberg scaling. If I put more than 0.5, it collapses again in the other sense. And there's this quite very interesting scenario when it's 0.5. And I get a suboptimal result. However, it doesn't depend on the beam splitter. And we can actually explain this. I mean, it was reported in the literature that this input state is quite special. And it was reported first for a balanced beam splitter. And then I think the Kim also reported for the unbalanced one. Anyhow, last year I also proved that this is the only one that yields a separable output. If you put 2 squeezed vacua, that's the only combination that you can get to obtain a separable output. Now let me summarize these results graphically. It's way easier to see. So if you have a resource, a total number of squeezed photons, if you have no external phase reference, the best you can do is just give them the same power, both. And then you get a flat result. You see it's horizontal. It doesn't depend on your beam splitter transmission coefficient. Now, of course, if you don't do it, you can put unequal powers, then of course the optimum will be in the balanced case, as you see in the blue graph. Performance is lower. Now, if you have access to an external phase reference, I plotted just one case. Immediately, the best one is totally unbalanced. You go again to the same situation we discussed before. Just shovel in the squeezed vacuum into your sample, just homodyne it or something, and that's it. If you force the same power into both, once again, you get a flat result because, as I showed before, it doesn't depend on the transmission coefficient of your beam splitter. Now, can you reach these results? Yes, and we know very well, for example, that parity is going well. Even the difference intensity works. However, you have to be far away from 0.5 because at 0.5, it just doesn't work. And once again, you have this quadratic homodyne detection that works just pretty well. So that's pretty much it. So we tried to optimize. We picked two input states which we thought important. Now we could prolong this study to other states. For example, squeeze coherent. Sorry, this is the first one I mistyped. It's coherent plus photon subtract the radiated photon. We thought of using two parameters for squeeze coherent plus squeezed vacuum. And then, who knows, if we have time and energy, we could try to attack more complicated states. So thank you for your attention.
Thank you. Are there any questions from the audience?
I have one question.
Please.
Go ahead.
Thank you for your talk. My question is there any recipe to derive expression for quantum Fisher information?
I'm not sure what you mean by that. What do you mean by recipe?
So how do you obtain the quantum Fisher information formula from which inputs?
Okay. Let me go back to. Sorry. Yeah. So if your input state is pure, the quantum Fisher information is just trivial. It's 4 times the variance of the operator that's just before your phase, right? So that's quite easy. Now, if it's not pure, you have to use what's called the SLD, so symmetrical logarithmic derivative, and things are a little bit more complicated. For example, for Gaussian states, you still have formulas. If not, it's more complicated. Then what I used here is just the same thing, but 4 times, right? I have to actually 3 times because FSD and FDS are equal. So I just apply the same thing. So computing the quantum Fisher information is straightforward. I mean, it's straightforward formally. It can be extremely long and tedious, but conceptually, it's just a variance. You just look what operator is relevant for your phase you're discussing. You just compute its variance. I mean, it can be extremely painful. Don't get me wrong. Look at my paper with Karunesh last year. I mean, calculations are horrible, but it doesn't mean technically, I mean, conceptually, it's not difficult. It's just very long, very annoying, but it's a variance, right? So that's basically what the quantum Fisher information is. And yeah, these are the 2 formulas I applied on and on in this talk.
Thank you.
Welcome.
There is a question from Vincenzo. Please unmute yourself.
Yes, thank you, Stefan. So, I had you were mentioning about that an optimal measure can be the square of the quadrature value.
Yeah.
Can you expand? How did you find that? Did you calculate the estimator?
Well,
To saturate the quantum Kramer
actually, I mean, actually, we found, so the operator is like you see here, right? So it's x, and we took x squared. Now, what they did, for example, the others here in the paper, in the PhysRebel papers, is not exactly this, something similar. So does it saturate? Yes. Can it reach the quantum Kramer bound? Sometimes yes, sometimes no. The problem is, for example, if you don't have an average value, homodyne just doesn't work, right? It's very hard for some input states. And then you have to invent something. So this is the trick we used for this. I'm not convinced this is the best. Maybe there are other detection schemes that we should have tried. But the focus was not on the detection scheme, right? So the question was really how to optimize an input state. And then it was like an accessory question, can we also reach what the QFI is doing? I mean, the guiding behind was the QFI, and the fact that we also showed that we can actually measure it was a sort of, to be sure we're not just proposing something that's purely theoretical.
So say it again, how did you show that you measure it? Did you calculate the Fisher?
Yeah, we calculate, I mean, what we did very long, I mean, Karunesh did this calculation for the QHD, for the quadratic BHD. So we just calculated the error propagation formula for this one. And yeah, we implemented the error propagation and we compared it with the quantum Cramer-Rao bound. And yeah, the results are, let me show again. The results are here, right? So it shows really good performance compared to the homodyne, just common homodyne, which is suboptimal, right?
In this, and did you reach the Eisenberg scaling with this?
Sorry?
Did you get the Eisenberg scaling?
Yes, you get the Heisenberg scaling with this one.
Okay, I see. All right, thank you. And but maybe just one little thing. You said that you have. Do you need to have the two squeezer out of phase of pi?
I mean, okay. Let me get this straight. So if you use the convention of the beam splitter I'm using, meaning this, right? So basically, I'm using complex R, right? Some people use T minus R, right? You have to somehow make either a Q beam splitter or what's called a thin film beam splitter. We use the thin film beam splitter. So if you use this beam splitter and then you go to the double squeezed input, this is the phase matching conditions you get. If you use a Q beam splitter, then it's 0. Right. Okay. In this PhysRev paper, which you see there, in 2019, I actually discussed also this situation with the phases. You find the section where I discuss how to adapt the phases in case you don't use the same beam splitter I'm using. I mean, I'm basically using this beam splitter because theoretically calculations are more simple. You don't have to pay attention when you put the minus or not. You have an eye and that kind of takes care of it. But if you're just not happy with this, you can use the other one. Then the condition morphs into theta minus phi equals 0.
All right. And you calculate the Fisher information for a model.
Yes.
And that saturates the quantum Fisher.
Yes. It's not Fisher. I'm going directly to the quantum Fisher.
Because for the measurement, for the quadrature measurement, did you calculate the Fisher information?
For the quadrature measurement, we didn't compute the Fisher information because probably it's too complicated. We just went directly with the error propagation formula.
Okay. Thank you.
Welcome.
Thanks.
All right. Thank you very much. I think in view of time, let's move on.
Thank you very much.
Thank you very much for your wonderful talk. Yeah. Our next speaker is Professor Sandor Bajo.
Yes.
Please share your slides.
Yes, just a second.
And you can start as soon as you're ready.
Yeah.
Today we have a lot more room for flexibility in terms of time, but tomorrow we are very tight in terms of time management.
Okay. So
otherwise you will miss the plenary. Yes, please go ahead. Yeah.
Okay.
Might be good. Yeah.
Yes,
okay.
Full screen. Yes. So thank you very much for the organizers and for the chairman of this present session to include my talk to this program. This is about that's a theoretical talk and is about theoretical machinery. Theories is always happy if has various tools to handle various phenomena. So, and now I'm talking about this phase coherent state formalism, which I I worked out a couple of years before, because in the meantime, I realized that it can be used for various other things as originally was invented. So this is the outline. So first, I would like to talk about a few words about this formalism itself. And then this is the new result, which came out just recently, when you can derive from these regular phase coherent states the so-called weighted Bernoulli space, which is a special Hilbert space, which can be used to use analytic functions to study SU11 groups. So then SU11 is very important in squeezing and parametric processes, etc. And then I will talk about a little bit the exact matrix elements which one can derive for between number states of the non-degenerate parametric down conversion evolution operator. That's interestingly, I have not found it in the literature. And in the last part, I would like to apply this general formalism for many parametric down conversion. So first, let's just speak a little bit about very briefly the phase operator problem. I started from this. So the basic problem is that, as you know, every complex number can be written down in a polar form. Now, the question is whether can one do it in quantum mechanics for an oscillator. And unfortunately not, because this, so if this is the absorption operator, and if you take the square root of the number operator, and here you have something which is the pure ladder operator. That's a partial isometric operator, not, which means that you cannot find a Hermitian phase operator. So that was the original motivation for all this study. And the other, the other problem is that you cannot express this A by just dividing with the square root of the photon number, because that has no meaning at the vacuum state. So the word regular phase coherent state, so the regular is just to avoid this difficulty, refers to this. Okay, and classically, as you know, this is a phase, classical phase expressed with
We lost you at some stage.
Yes, it seems to me also.
Yeah. It seems like we can't hear you. So, Vaho, you still there? No, we lost him. Maybe you should quit and come back. It seems there's some problem. Do you hear? So maybe we can move on to Sebastian Padua and see if Professor Vaho can join us later on.
Okay.
Sebastian, you can start if you are ready.
Okay.
And hopefully he'll join us in view of time. Thank you. So our next speaker is Sebastian de Padua. I hope I got it right.
I'm awfully sorry for the collapse of the night.
We move on to the next talk, and then we'll come back to you later on.
Yeah,
if you don't mind.
good. Yes, of course.
Thank you.
Of course.
Thank you.
I had to log in, etc. again.
That's right.
Continue.
That's right. Yeah. Continue, Sebastian. Yeah.
Okay. Can you see my slides?
Yes, I can see.
Yes.
Okay.
Yeah, please.
Okay. First, I would like to thank you, the organizers, for. Oh, sorry. Okay. First, I would like to thank the organizers for the kind invitation for this traditional conference. So the title of my talk is Quantum Coherence and High Dimension Complementarity. I'm from the Federal University of Minas Gerais in Brazil. So I will talk about first quantum coherence and some measurements that we did. Quantum coherence is a property of a quantum state system. Its measurement depends on the observation of the interference pattern between the vector states components of the system. But you have to be careful because the interference pattern observation requires a path marker being in a superposition state, such that the detection system is unable to distinguish the state component in which the system is, as first discussed by Englert in this work. So in our case, we prepare the states just by crossing photons by a multiple slit. The quantum coherence measurement is done by measuring interference patterns, use a lens, and detecting at the focal plane of the lens, or at the also Fourier plane, because at this plane here, the lens does an optical Fourier transform of the aperture. The observation of the total quantum coherence of a qubit state, in this case you prepare a qubit state, depending on the number of apertures, you change the dimension of the state. The observation of the total quantum coherence of a qubit state is viable only in the condition that the possible path marker states are massively indistinguishable. This happens when the Fourier plane, the focal plane, coincides with the detector plane. So we are going to label the photon path states in this way. For instance, for a triple slit, we are going to call the slit as -1, 0, 1. If you have two slits, we are going to call -half and half. The density operator can be written as usual in this way in terms of these photon path states, where lambda in general is d-1/2. Rho LM is the set of the density matrix coefficients, and J is the state of a photon transmitted through the aperture J. So quantum coherence is a property of a particle state being capable to produce interference in the count probabilities. It depends on the non-diagonal elements of the density matrix. If you expand the density operator in terms of this way, such that you can see the diagonal elements here and non-diagonal elements here, So the quantum coherence depends on the non-diagonal elements. And it can be measured by, if the measurement apparatus cannot distinguish the base states, as I mentioned. And this was discussed in these two articles. The first one I already mentioned by Englert, and also this second one by Bera, Kirish, Siddiqui, and Patti from 2015. So just to review this requirement, suppose you have the states here, that you have a superposition state, and then you have the pass marker states, and then you are going to detect in some place the superposition, some plane, the superposition states. So this is the density operator initially. Now you can write the density operator with the pass marker states. And if you are going to observe, you want to observe only the superposition state, you have to calculate the reduced density operator, tracing the states of the pass marker. And then when you do that, you see that you have here the inner product between the pass marker states. So the pass marker states must be non-orthogonal, otherwise you get 0 here. And they are 0 when the inner product is, if they are orthogonal, the inner product is 0. And this is the bad situation. That's what you have if you detect at the image plane. Then you can identify in our optical setup the photon pass. But we want this situation that occurs best in the Fourier plane. Okay, how to quantify the quantum coherence of a quantum state? For the bidimensional quantum state, this was done in a very nice work by Mandel, this very nice paper here, a 2-page paper, Coherence and Indistinguishability. And he shows that now you have, in this case, you have only one non-diagonal element here, and by looking at the visibility of the interference pattern, you already measure the model square of this non-diagonal element, and you have a measurement of the quantum coherence. Now, for high-dimensional states, the situation is a little more complicated. States with dimension larger than 2. Again, I show the density operator written in terms of the diagonal elements and the non-diagonal elements. And then this work from Baumgratz, Kramer, and Plenium from 2014, quantifying coherence, show that the L1 norm, it's a good measure for quantum coherence. And this is defined by this term here, depends of the dimension, and the sum of the modulus of the non-diagonal elements of the density operator. So how to measure this experimentally? If you have a bidimensional system, as we have seen, is simple. You just look the interference pattern, and from the visibility of the interference pattern, you get the measurement of the quantum coherence, because you have now the access of the models of the non-diagonal element. But for high-dimensional states, how to get this sum here? So first, let's look in our case what happens at the Fourier plane, the focal plane of this lens. You have interference here, and then from this density operator here, we can calculate the probability to detect the photon at the Fourier plane, at the optical plane. And what you get is first the usual sinc function square here, that it's from the diffraction of the apertures of the slits. And then you have another term that depends on the diagonal elements. And the second term with a oscillation that correspond to the interference, multiplied by the modulus of the non-diagonal elements. And so this is the good part that we intend to extract the coherence map. So we want to get this sum here. to get the coherence as proposed by the plane work, Baumgras and plane work. So then we use this method here that was proposed by Tanya Poe and Tabish Quresh in 2017. What they propose is that you measure this quantity here that I call theta. That is the difference between the probability to detect at the interference pattern at the Fourier plane, as I just mentioned, minus another term here that is produced at the Fourier plane by an incoherent source. So if you have an incoherent state, and you just, if you have an auxiliary source with a coherent state, photons in a coherent state, then you detect this probability with this auxiliary source. And then if you make the difference between the two functions and divide by the diagonal, you get theta. And theta you have oscillatory function here that which the amplitude depends of the modulus of the non-diagonal elements, where gamma is 2 pi over lambda, d the separation between the slits, and f is the focal length of the lens. Let's see one case for a Q3 system. For the Q3 system, you have this the density matrix in this way. Those are the non-diagonal elements, depends of the phase. This phase is here between the slits that I'm labeling -1, 0, 1. Now, if you calculate this theta function for this situation, you get these 3 oscillation functions. 2 of them have the same period, depends of gamma that I just mentioned, and one of them depends of 2 times gamma, correspond to the interface between these stream slits here. And in the case where the phases are 0 or pi, you see that the coherence, it's the maximum when all the phases are equal to 0, or the minimum of this function when all the phases are equal to pi. So I plot here this function for the case where all the phases are 0, and you see that the maximum correspond where it's written blue here. Sorry. It's shown, it can be shown that is the sum of the models of these elements multiplied by 2. And if you have pi phase, all of them pi phase here, and then the quantum coherence equal to the minimum of this oscillation. But if you have different phases, then the situation gets complicated and you cannot extract the coherence measurement. Like here you have pi over 2. In others, even when it's not 0 or pi, or in this situation we have different phase here, you get this oscillation. So this was discussed in this work. So how we did the measurement? First, we have a spontaneous parameter non-conversion source. We produce photon pairs collinearly. One of the photons cross a double slit, and another photon cross a triple slit. And the one that crossed the double slit, we detected the image plane, and you have a Bakhtin detector. So that's how experimentally we implement the reduced test operator, because we are detecting with the Bakhtin detector here that cannot resolve the interference pattern. And here we have a point detector, and this one we are going to now measure the interference pattern of the triple slit condition to detect of the photon here at the Fourier plane. And now I don't have time to explain, but we could prepare some simple triple states in this scheme by changing the optical system before the PS here. That this is explained in this other work of our group. So we could prepare these two states. You see this state here, first the phases are all zero, and the non-diagonal elements in the first one, I, we have whole one. We have two different non-diagonal elements, and this one here we have only one non-diagonal element. And the function proposed by Poe and Kuresh, they are very simple. Now you have only one oscillation function, and the amplitude depends on the sum of the models of these non-diagonal elements, and the other one depends on only one of or only one of the one that you have in this state, non-diagonal element. These are the experimental results. First, we didn't do what was proposed in that work. We didn't use any extra source to produce the incoherent state. What we did was we blocked two of the slits of the triple slit, and we detected at the Fourier plane the photons crossing for only one of the slits. And we did that for the three slits. And then we summed these counts, and you got this red curve. So these red curves correspond to the probability to detect the photons when you have an incoherent source. And the black is the probability to detect the photons in the interference pattern. And then you subtract both, and you get this oscillation here for the two prepared states. And what we see is that for these two prepared states, you can do it different ways. You can fit the interference by using a fit of the interference pattern using the oscillation function proposed by Poe and Kuresh. And also you can look at the massman of those peaks, as I mentioned, have different system here, you'll get similar results. Now, suppose you have a more general situation. I was just mentioned that you have now different phase. Then there is one way that you can measure coherence, we use in other works, is that you just block one of the slits, and then you see the interference of the two of the slits. In this case, you come back to the situation of the bidimensional situation where the visibility gives the coherence. And then you do that for all the pairs of your QD states, and you can sum this partial coherence, let's say this way, and you get the total coherence by using a proper normalization. This is it can be demonstrated. So that's a general solution. And these are just mentioned, I don't have time. This was a work that we proposed a photonic circuit to measure quantum coherence for a general QD system. Now, the second part of my talk, I have a few minutes. I will have to rush. I'm going to call quantum coherence distribution and high-dimensional complementarity. This is a theoretical work. We investigated the complementarity between the LE1 norm of quantum coherence, linear entropy, and predictability of any d-dimensional discrete quantum state. And we show that they are connected by a force variable quantity that we name T. So let's start with the density operator for a QD state. And the linear entropy is a measurement of the mixedness of the state. You it depends of all the elements of the density matrix. The predictability, it's a measurement of the photon pass in some interferometer, depends of the diagonal elements. And the normal, I'm sorry, here it's wrong, it's the norm L1 coherence, the quantum coherence measurement, as proposed by Baumgart's plenum. It's comes from the L1 norm of the vector W, composed by all the n non-diagonal coefficients, and depends of the modulus of the non-diagonal elements. Now we start with what motivates our work. Jacob and Bergou obtain a complementary relation between the linear entropy, predictability, and quantum coherence. In that case, they don't use the norm L1. They use this V measure, generalized visibility, that at that time was thought that was a good measurement for quantum coherence. And they got this nice equality here, complementary relation. This generalized visibility now depends of the modulus square of the non-diagonal elements, and is proportional to the L2 norm of the vector W, composed by the n non-diagonal coefficients of O. But in 2014, Baumgart's and Kramer and Plenum showed that this is not a good measurement for quantum coherence. So then we thought to try to fix this inequality here by changing V square by the norm L1, the new measurement proposed by Baumgart's, Kramer, and Plenum. So let's go back to the linear entropy, predictability, and the norm L1 coherence. So if we calculate S squared plus P squared, what we got is that, and try to add the norm L1 coherence, we got this expression here. So you see that now you have this good quantifier of quantum coherence, the linear entropy, and the predictability, but you have another term here, T. This term here, T, is a variable that is dependent of whole non-diagonal coefficients such that is written this way. So what we see here is that it depends of the product of the non-diagonal elements of different non-diagonal elements. So it seems complicated, but it's just a sum of the product of the non-diagonal elements of the disk. Now let's discuss a little bit the meaning of this T. So if we start with the inequality, the equality derived by Bergou, and the one that we derived, we show that the quantum coherence by the norm L1 can be written in terms of the generalized visibility and this T term that we found. Now, if you use the relation between the norm L1 and the norm L2 square, where n corresponds to d squared minus d, the number of the non-diagonal elements, and we saw that the c square is related to the square of the norm L1, and the v square is related to the square of the norm L2. We see that this term T is smaller than the quantum coherence measure and depends of the dimension of this. Now, from the expression, the complementary relation that we derived, and from this bounding of T, we see that the c squared plus s squared plus a squared is not equal to 1, it's smaller than 1. And the equality holds when T achieves its upper bound. So I comment some physical meaning of this T. T depends of the multiplication between the absolute values of the two different non-diagonal coefficients of the density operator. It's proportional to the sum of all pairs combination of non-diagonal coefficients. T is undefined for dimension T. Is undefined for dimension D equal 2, since a density operator in this dimension has only one non-diagonal element. For other dimensions, for qubits in general, T is different from 0 if the density operator has at least two coefficients, since you have the multiplication of two different coefficients, different from 0. A quantum state with all models of the non-diagonal elements equal the same values present the same partial coherence for all pairs ij. In this case, we can say that quantum coherence is uniformly distributed in the system. So T indicates the quantum coherence distribution among the levels of one partite system, being a non-entropic quantifier. So that's the meaning of T. T is a good quantifier of the quantum coherence distribution between the levels that form the qubit state. So I arrived to the end. And just to mention here the collaborators of this work. First, here in red, Paula Machado, that this work is her PhD thesis. She did most of the work. And we have as collaborator Carlos Monken, Arthur Matoso, and Leonardo Neves. Thank you.
Right, thank you. Any questions? A quick question from the floor before we move on.
One question.
Yes, please go ahead.
Yeah, thank you for your talk. Clarification. Off-diagonal elements of density matrix are responsible for coherence. So if off-diagonal elements are 0, then due to decoherence, density matrix is in the mixed state. So my question is, what other benefits one can have knowing value of coherence?
Can you say again?
What benefits does one get from coherence?
Okay, so coherence is a measurement of, it measures the property of interference. So it's different from purity. You can have a pure state, but it's not capable to do interference. And you have many protocols that you need superposition. For instance, quantum Fourier transform, you need superposition. But you have more formal works that have shown that coherence restores quantum coherence. So I'm sorry if I didn't answer.
Yeah, it's clear. Thank you.
Okay.
Right. Sorry, Sebastian. Perhaps we'll move on because in view of the time, and invite Professor Vaho.
Okay. Thank you.
Thank you. Thank you very much.
Yes, thank you very much. So I'm awfully sorry that somehow there is a problem with the network. Yeah. Okay.
Sorry, it's okay. Don't worry.
So yeah. Thank you. Now let's proceed. So I stopped here, or I was stopped here. Now okay. let's have a look at the absorption operator. Now, if you put a positive number here, then you can divide and you can express the exponential, a new exponential phase operator with the absorption operator. So this was the formal thing, very simple looking, but then by Fourier correspondence, you are able to construct a Hermitian phase operator. And what I did in this work I found the coherent states of this new exponential phase operator, which looks like that here. And this, in fact, is an S1 parallel coherent state. And I compiled the diagonal representation, and then I encountered with the kernel function of this Blaschke function, where B is a complex number in the unit disk. You see? So, and then this kernel function behaves very nicely because for large excitation it reproduces this sawtooth function, etc. So here are the formal detail. So these eigenstates of the exponential phase operator, on the other hand, can be expressed a la Perelomov with the unitary transformation, where these are the group Lie algebra elements of the S11 group. And in our case, these K and K dagger are expressed by the original absorption and number operator. You see? So this is the S11 group. Just to summarize very shortly, in our case, the generators look like that. And this is the Casimir operator, and the Bargman index is defined this way. In our case, that is this quantity. Now, nu can be any positive number, so, and all the physics is coming from fixing this nu. Now, anyway, that's nice that it has, so for instance, the photon number distribution in this state is a negative binomial distribution, which came into view recently in the context of parametric down conversion. I am sorry if the converter did not show this properly on the axis, this thing, but let me just show you that these coherent states, phase coherent states, are not diagonal, not orthogonal. However, the product can be expressed by a so-called Blaschke function. And this looks very similar to a multiple interference figure. Here I plot for the same modulus values various phase differences of these two complex numbers. So this is an interference. And so the Blaschke function in general looks like this. So Z is in the unit disk, T, capital T, is the circle, and this epsilon is a number of unit modules. So we have three parameters altogether, and these Blaschke functions are playing very important role in the theory of functions. And at the same time, this is in another context, it is called the Möbius function. So it maps, this is the Möbius map essentially, when you map Z to some other complex number. Okay. And this has a nice group properties. So if you apply consecutively these the multiplication rules, and you can also generate a function operation by just defining the application of the functions consecutively in this way, and then you get another group which has the same structure as the original one. There is a R integral, invariant integral, etc. So now let's discuss further. That's very nice that if you introduce in the complex unit disk this weighted area measure, and you have our coherent phase coherence state, and you take the scalar product of any Hilbert space element, then of course you have a function which depends on this Z parameter. And from the completeness relation, you can nicely derive such a reproducing formula, where the reproducing kernel is essentially the so-called weighted Bergman kernel. And these functions form an analytic, the Hilbert space of analytic functions, which is called the weighted Bergman space. So, and for instance, a unitroid transformation, which we will encounter later, it acts on an element in this way, which means that it puts to the argument of Z the Blaschke function of Z. So that's a nice correspondence in mathematics. There are many results concerning weighted Bergman spaces. So here we derive it from the regular field structure. And that's also very remarkable that if once we have this unitary operator which generates this Z from vacuum, this is the more general, is that forms a group. And interestingly, the exponential phase operator, it transforms the exponential phase operator Möbius expression. That can be shown explicit by explicit calculation. So that's very nice because that's a nonlinear expression. And now let's apply. So for instance, we take degenerate and non-degenerate interactions in the parametric Dine conversion, which you have for squeezing. Here the generators look like that. So A dagger square and A squared. They satisfy this equation, Lie algebra, close to Lie algebra. And for non-degenerate case, you have the two photomodes.
So sorry, I think we lost you. Yeah.
Yes.
The connections to Hungary doesn't seem very good. Is it Hungary? Maybe. Let's wait for a 2 minutes or so. Is he back? So Sebastian, actually some time ago, or actually many years ago, 20 years by now, we actually formulate entropic inequality of qubits. I think it was at that time.
Okay.
Together with Berger and England. Oh,
Good.
It's back. Yeah.
I am awfully sorry, but this is so. Yesterday it worked perfectly. I don't know what's the matter.
Well, it's you try and share your slides.
Let me. If next it collapses, then I won't come back, of course, because this is already too much. I mean, this is okay. So let's share. Let's share. Where is it? Share. Screen share. Yes. Yeah, this is slightly embarrassing. View to screen mode. Now let's see. So, okay, so in case of the non-degenerate case, you have this the simplest situation, 2 modes, A and B, and then this is the evolution operator. And you can nicely build up a similar A and capital N just by this correspondence. So you have 2 modes. On the other hand, in this situation, the Casimir operator, which is the difference of the photon numbers, is a constant. So and you can fix these, the modulus of n1 minus n2, and you put nu. So here the physical significance of nu is this number. And then you can use the same Lie algebra, everything, but of course the Hilbert space is slightly different. And that's nice that you can calculate the in complete generality, the matrix of
We seems to have lost you again.
Yes.
You got frozen. Is he coming back? Yeah, because let's see if he comes back. Maybe you can ask him to summarize. He said he's not coming back.
Yes. Let us see.
Recording stopped.
Okay, so maybe we stop here, and thank you very much. A round of applause to all the speakers today. Thank you very much for coming to this session. Thank you.
Thank you. Bye.
Thank you.